and welcome back to my channel. I am feeling a little sick today, so I'll be sipping on my Theraflu. But today I'll be doing actual client work instead of a COMSOL tutorial. So since I had to do it anyway, I figured I would record it and make a video out of it. So I've already done part of the problem. So let me show you the input. Here's the input. The problem that we have is to do a 2D modeling of an electric field given a sphere with two electrodes on the sides that cover 45 degrees from the center. So this one is 45 degree coverage, and so is this one. And there's a layer, sort of like a balloon, is how you could think of it. So the outer diameter is 210 millimeters and the inner diameter is 200 millimeters. So it's a 10 millimeter thick sphere with some medium in the middle with these properties. The sphere layer has these properties and the electrodes has these properties. So this is, let's see. He just provided the symbols and I was able to figure out what the the parameters were. So let's see. Sigma is in units of Siemens per meter. So I think that was electrical conductivity, and then was that one epsilon? Relative permittivity, epsilon sub r. So the sphere has 1 times 10 to the 5th, and this is dimensionless. And then the electrical conductivity is in units of Siemens per meter. So at first I tried to do this in 3D, and I was just going to take a cross section of it. But I realized that after I modeled the sphere with the outer and inner layers, I realized I don't actually have the full dimensions of the electrodes. So I am sort of forced to do it in 2D rather than modeling in 3D and taking a cross section, because I would just be guessing, you know, how long are the electrodes around the sphere, etc. So that was my first attempt, and I'll show you the next attempt I did. Here is the geometry I came up with. So we've got a 1 millimeter thick electrode on either side, and then the not an annulus, just a spherical layer here, and then some, I don't know if it's air in the middle or vacuum. We're just given the properties. So some material in the middle of the sphere. So for the tutorial purposes, I'm going to recreate this, but just to show you what the results will look like, here's the electric field norm in volts per meter and the electric potential in volts. Okay, so there's going to be 3 plots like this. He wants one without the center electrode. So it has the same material as the electrodes on the side. This one has a positive 10 volts applied, and this one has a negative 10 volt applied. And then we've got one electrode in the center that's 20 millimeters long and 1 millimeter thick. Okay, so these are the surface plots we're going to produce, and I'm going to do this again from scratch. So let's make this fill the screen, and we're going to do Model Wizard 2D and choose magnetic fields, which is under AC, electromagnetic fields, MF. And interestingly, this physics is only available in 2D. It says it's supported in 2D and 3D, but when I tried to do it in 3D, this one was not available. So I'm not sure what the difference is. It says depending on your licensing, it's available in 2D and 3D. So I don't know why that is, but this is only available in the 2D. I'm going to do a stationary study instead of a frequency domain study. So I'll select that and then do done. And now we start with geometry. So first we're going to build the shell or the sphere cross section. So we'll go to geometry and click circle. So we're given the inner shell has a diameter of 200, so the radius will be 100 millimeters or 0.1 meters. And the outer shell, so I'll do another circle, just click on circle again. This one comes up as circle 2, has diameter of 210, so that's 0.105 meters. All right, so now we have 2 circles. My eyes keep watering. Okay. So now we want to add a material. Let's see if I can do this. Materials, add blank material. So right click on materials and hit blank material. Oh my god. Okay, and now for domain 1, I want to delete domain 2, so I'm going to select it here and hit minus, because this came up automatically with both domains. Now only domain 1 is selected for this material. Alright, so I don't need I don't need relative permeability, so let's see if I can remove this. Oh. We don't need that one, but we'll just leave it blank for now. So for the electrical conductivity of the sphere material, we're given, let's see, this one is in units of Siemens per meter. So that's the 44 for the sphere. Electrical conductivity of 44 Siemens per meter, and a relative permittivity of 1 times 10 to the 5th, dimensionless. So we just write 1E5, the syntax there, so that saves. And now we want to enter another material for the inner domain. Blank material, domain 2, and we're going to give this one a 2000 and 0.015. Okay, so 2000. Oh, I think I entered the wrong field in the last one. Unless these were in a different order. So it's got electrical conductivity. Oh, hold up. I switched those. This one is 0.015 Siemens per meter, and this one is 2000. Yep. Epsilon rho is 2000, and sigma is 0.015 Siemens per meter. You just double check this one. Yep, that one is right. And now we need to add the electrodes. So let's go back to geometry, and we're going to add another circle. So as you can see from the document provided by the client, the electrodes are 1 millimeter thick. So that means if the surface of the outer sphere is 210, then this will extend to 211. And then it stops right on top of the sphere. So we're going to have a radius of 0.106, and it's 45 degrees sector angle. So let's build that one. So you get this pizza slice over here, and then we're gonna do a difference. So let's create another circle with radius 0.105, which is now the radius of the sphere, because that's where this one stops. Sector angle 45, build selected. So you can't really discern it, but you can kind of, highlighting both of them, you can see the difference. So now we're going to do booleans and partitions, difference. And first select the one to add. You'll see circle 3 pops up, which is the larger pizza slice. And click objects to subtract, and click on circle 4, which is the inner pizza slice, and then build selected. So now you can see we're left with only the 1 millimeter thick electrode on the outside of the sphere. I just hit zoom extents to go back to the view. So now we have this side, we got to create another one on this side. Alright, so we're going to do the same thing here with a new circle. Circle 5, this will have radius 0.106 and a sector angle of 45. But now for the rotation, we're going to put in 3, I think it was 335. That's what it came out to. Oh, nope, that's 135, so that's what it was. Yeah, so that'll make a perfect, so like in this one, it looks like they're completely across from each other on the hemisphere. So that's how I'm making this one. It's completely across from the 45 degrees. If we rotate the angle 135 degrees. Okay, so there's the first one. Then we're going to make a new circle, circle 6, with radius 0.105, sector angle 45, and rotated 135 degrees. Okay, so now you've got a, if you zoom in, you can see this is the larger pizza slice and this is the smaller one. So now we're going to create a difference. So booleans and partitions under geometry. Difference 2 pops up. First we'll select the objects to add. So the larger pizza slice, highlight objects to subtract, and select the smaller pizza slice, and then we're left with the difference, which is this 1 millimeter thick electrode. Now what I haven't done yet in the last model, but I will in this one, is create these center electrodes. So this little thing in the middle. So we're going to have one horizontally located and then change it to be vertically oriented, and do simulation both ways. So it looks like a rod. So I could either go with ellipse or rectangle. probably just I'm gonna go with ellipse, see if we can do that. Okay, so for the ellipse, we'll put in the horizontal length is 20 millimeters, so 0.020 meters, and it's a millimeter thick, so 0.001 meters thick. A rod, honestly, is probably more like a rectangle with just a rounded end, and then we have to give all of these electrodes a material. So I'm going to go to materials, right click, blank material, select the domain. So here, oh no, that's not what I want. Let's see if I zoom in. Yes, there we go. Domain 5, 2, and 1. So these are all the electrodes, and they all have the same material, which is a relative permittivity of 1E5 and, oh wait a second, did I enter that wrong earlier? Oh. Okay, I entered this is the material for the sphere layer is 205 and 0.015. I entered the electrode material. So we'll change that, but right now I'll enter the electrode material relative permittivity of 1E5, or sorry, that was relative permittivity, not permeability. 1E5, and then electrical conductivity of 44. And then I need to go back to material 1, the sphere layer, and change this one to the 205 and 0.015. Okay, so those are all in correctly. I don't know why they appear in different orders. Electrical conductivity comes last for material 3. But anyway, so we've got all those in. Now we're going to go to magnetic fields, right click, and add let's see. We need to add the 10 volts and negative 10 volts on the electrodes. So that's going to be the oh, you know what? I picked the wrong thing. So my mistake, I added magnetic fields instead of electric fields because my brain is not working right. So all you have to do, if you had the wrong physics, just delete this physics. I was wondering why the condition I was looking for didn't appear. And then go to physics, add physics, and then look for the one you actually want. So it's electrostatics, which should be under AC/DC, electric fields and currents, electrostatics. Add to component 1. Okay, there we go. So now I'm going to right click on electrostatics and add electric potential. And then click on this electrode. So domain 20, and oh wait a second, that's just the boundary. Okay, so I need to select all of the boundaries of that electrode, and we're going to add an initial voltage of plus 10 volts. I'm going to do the same thing for the other electrode, add electric potential for this, all four boundaries of this electrode of negative 10 volts. Let's check the initial values. So, 1, 2, 3, 4, 5 all have an initial value of 0 volts electric potential. So when we turn on at time 0, then the electrodes will have a electric potential difference. Let's try to check the 0 charge. So those are fine. Charge conservation, those are fine. We'll go to study, or no, sorry, mesh. Mesh selection is next. So we're gonna do user controlled mesh, sorry, physics controlled mesh. And I did normal initially, but for this one I want to try finer. And let's click build all. Okay, so here's the mesh. And now let's go to the study. So under study 1, step 1, stationary, I'm going to click compute. Okay, so that was super fast. That took like 3 seconds, 4 seconds study time. And let's just double check. Alright, so one thing is for the electric field norm surface plot, you have a lot of gradient here right under the electrodes with the voltage potential, electric potential, but you don't have much of a difference shown inside the sphere. So I'm going to see if I can change the color plot, the legend. Okay, so since I want to capture this before changing the geometry, I'm going to go to my surface plot and take a screenshot and call this E-field 2, since I have my E-field 1 is the one without an electrode in the center. And save, then bring up my streamline plot, or sorry, my electric field norm surface plot, and take a snapshot. Okay, so to save the other one, I'm going to go to export, image 1, and under output, target file, PNG, file name. Let's browse. I want to put it here, and we're going to call it E-field 2A. Since we got 2 surface plots for this one. Now that that's done, I'm going to go back to my geometry and change the orientation from horizontal to vertical for circle 5 and, for ellipse 1. So we'll just change this from 20 millimeters to 1 millimeter, and this one from 1 millimeter to 20 millimeters. Okay, so now the rod electrode in the center is vertical. And we're going to go to stationary again and hit compute. Alright, and here's our electric potential and our electric field normal. So I'm going to save these. Let's see, no, it was under coloring and style. I had spectrum. I think I had a prism dark selected. Just because it made it a little more obvious. And then I just slid the color calibration parameter all the way over to the left. So it makes the closer to 0 values a little bit more purple instead of just gray, so there's more of a gradient. It's still pretty near 0 in the center. So the values haven't changed, just our color legend. So I'm going to create an image for that. Okay, so that completes today's video, and this was a tutorial on how to do a 2D simulation of an electric field of a sphere with 2 electrodes and a positive 10 volt and negative 10 volt differential applied. Thanks for watching, and hopefully next video I won't sound so nasally.